So we can kind of get started. So what I'll go over today, basically everything we've gone over with elimination thus far, and then what we started with on carbocation rearrangement. Did everyone sign the sign-in sheet? Not that it really matters, but thank you. Okay, so beta elimination is what we started with. This is a type of elimination reaction where a leaving group and a hydrogen from an adjacent carbon. So two groups from two adjacent carbons are eliminated, and you form a double bond between them. So it requires a good leaving group and a base, a strong base, which we'll typically use an alkoxide or hydroxide. And these reaction also requires heating because bonds are being broken and it requires energy to break bonds. And here I have a compound, this one in green. This is the alpha carbon because it has the functional group attached to it, and the chloro group is the functional group. The ones in purple beside it are the beta carbons, which are connected to the alpha carbon. And then the hydrogens on the beta carbons are called beta hydrogens. And these beta hydrogens are the ones being eliminated, as well as the functional group. So what we spent the most time on is dehydrohalonation, and this is a type of beta elimination. And this is just where the leaving group is a halogen, so either chlorine, bromine, or iodine. And then also a beta hydrogen is eliminated as well. So the general reaction for this, you'll have your alpha carbon here with your functional group, which is a halo group, and dehydrohalonation. And then you'll have a hydrogen on the beta carbon. So this base will take this hydrogen, and then this will leave, and you'll form a double bond here. End up with an alkene, and then the base will form a bond with the hydrogen, and then this will come off as an anion. So we have two types of reactions. So this, as opposed to substitution reactions, it's not as cut and dry as SN1 and SN2 when you can kind of figure out which one you'll have based on a variety of factors. This one is a little bit more complicated. It's not as cut and dry. So you won't get as many questions about if it's going to be E1 or E2, like substitutions. Normally, if I remember correctly on the test, they'll tell you if it's going to be E1 or E2, just because it's not as easy to figure out which one to do. But E1 reactions, similar to SN1, they happen in two steps, and they have a carbocation. They can occur with secondary and tertiary substrates. Because you're making carbocation, you can't form primary carbocations. So you can only use secondary, tertiary. The rate determining step only involves the substrate, which means the rate determining step is unimolecular, hence E1. And for E1, you can use a lower concentration of base, even though for both these it has to be a strong base. A weak base won't work. So E2 reactions, they happen in one step rather than two. There's no carbocation. We can have this with all substrates. So as opposed to SN2, we couldn't have SN2 with tertiary because there's too much steric hindrance. But because E2 has this stipulation where they have to be anticoplanar, that gets rid of the steric hindrance risk. So we can have an E2 reaction with all substrates. The rate determining step involves both a base and a substrate, which means it's bimolecular E2. And we need a high concentration of a strong base for E2. And like I said, the leaving group and the beta hydrogen have to be anticoplanar for this to occur. So here's an example of an E1. So yeah, this substrate here, this is secondary. And then our base here is hydroxide. Like I said on the test, I'll normally tell you if I remember correctly at least, he'll tell you if it's going to be E1 or E2. Or he'll tell you like high concentration, low concentration, and that should tell you E1 or E2. But in E1, the first step is the leaving group comes off, and we make a carbocation here. And then your base will come in and take either the beta hydrogens. In this case, they're both equal. They're in the same environment, so it doesn't matter. There's no regiochemistry here. So it'll take either of the beta hydrogens from the beta carbons, and then these bonding electrons from the CH bond will go to form a double bond, and that will neutralize that positive charge here. So you'll end up with your alkene here, and then this base will form a bond with the hydrogen to make water. Chlorine comes off as an anion. So, E2 reaction example. So, like I said, they have to be anticoplanar. So the only way to tell if they're anticoplanar is if you're given this 3D structure. If you're not given this, if it looks like this, we don't know if they're anticoplanar, right? Because we don't know where things are in 3D space. So you need to have 3D structure in order to tell. But here we have the chloro group, which is their leaving group, and then these two carbons and the hydrogen, all in the same plane. They're all connected by a straight line, but they're on opposite sides of this CC bond. So this is anticoplanar. So what will happen is instead of making a carbocation, happens all in one step. So the base sticks the hydrogen. These bonding electrons from the CH bond will go to form a double bond here, and then the carbon-chlorine bond will break, and that'll come off. And here we form an alkene, and these groups just shift down, these ones shift up, and you have this alkene here. And again, we have water and chlorine. Make sense? So this is the important part. This is where you're going to have the most questions about radiochemistry and stereochemistry, about elimination reactions. So for E1, both radiochemistry and stereochemistry is determined by the stability of the carbocation and stability of the product. There's no kinetic control in E1 reactions. There's only thermodynamic control. The thermodynamic control, if you remember, is just the course of the reaction is determined by the stability. Kinetic control means that the course of the reaction is controlled by the speed. And then remember, regiochemistry is just studying which structural isomers will be the major product, and then stereochemistry is determining what stereoisomers will be the major product. So here's an example of E1 reaction where you have both regiochemistry and stereochemistry. So I've already drawn out the products here. So we have two, this are my alpha carbon here. We have two beta carbons on either side. So I can take this chlorine group and one of these hydrogens, or I can take chlorine group and one of these hydrogens. So that will give me these two products. This one would be foreign if I took this hydrogen here, and this one would be foreign if I took this one. So I'll go ahead and write out the first step of the mechanism. Okay, so the first step of the mechanism is still the same. The leaving group is going to come off first. And make a carbocation. Okay. And then my base comes in. So like I said, I could either take this hydrogen or this one. Which one's more stable?
More hydrogens equals.
Yes. Bottom one is more stable because it has less hydrogens around the double bond. And this is basically just because this is a lot of electron density here, and the more area it has to spread out, the more stable it'll be. So if I have more hydrogens, it doesn't have anywhere to go. But if I have more alpha groups around it, it can spread out and lower the energy. So this bottom product would be more stable. So I'm going to take one of these hydrogens. So lone pair of electrons from oxygen will take this hydrogen here. The CH bond will break. Those bonding electrons will go between here, form a double bond, and that will neutralize that positive charge. Okay, so this would be my major product here, which is more stable because I have less hydrogen around the double bond. But if you'll pay attention to the double bond here, I also will have stereochemistry here because I have two different groups on either of the double bonded carbon. Do you remember that from how to tell things will have cis-trans isomerism? If they have two different groups on the double bonded carbons, then they can have cis-trans isomerism. Do you remember that?
Yeah.
Okay, so this will be my major product, but that product has two different isomers, okay? So I could have cis, and I could also have trans. Okay, so which one would be more stable out of these two?
Trans.
Right. So this will actually be my major product because it's the most stable, and regiochemistry, stereochemistry. You look confused. Okay. Okay. So because the regiochemistry and stereochemistry of E1 is only determined by the stability, so you're just paying attention to which product would be more stable. And just be sure to pay attention if things can have stereoisomers. So just make sure you're paying attention to cis and trans.
When do we use E and Z combination?
So E and Z, so I can use cis and trans because I have, yeah, because I have, yeah. So say I have like,
Like when they're all different.
yeah, so all these, both of the double bonded carbons have two different groups on them, but they're not like comparable. I can't say like, oh, these are on different sides because I don't have any of the same groups. So then you would assign the priorities to E and Z. You can also still do E and Z here. It's not wrong to do that.
Would that be trans? I mean cis. That would be cis, right?
This one.
Yeah.
So because you have the different groups, you would have to use E and Z. Because you can only use cis and trans if you have the same groups on both carbons.
But would that be Z?
Can't remember which.
Yes. Yeah. Yeah. Because Z is higher priority groups on the same side, E is on different sides. Which is always annoying to me because Z like feels like it should be on different sides.
Kaylee said like Z same side. That's how you
Sure.
do
If that's how you want to remember it. But you can also use E and Z with this. It would still be correct if you, like this would be Z, this would be E, this would be Z. But you can only use cis or trans if they have the same groups on them. Okay, so E2, regiochemistry and stereochemistry. This gets a little bit stickier, just because it's not just controlled by stability anymore. So for regiochemistry, it is both controlled by the stability of the product, but also the bulkiness of the base. So bulky bases, you'll only have to remember this one. He won't ever give you any other ones. And in terms of non-bulky bases, he'll normally either give you hydroxide, methoxide, or ethoxide. So that is T-butoxide. And that's the only one you'll have to remember for bulky bases. Okay. And then stereochemistry is determined by the structure of the substrate, so we have to have that anticoplanar. We cannot have E2 unless we have the hydrogen and the leaving group anticoplanar. So, examples of this, regiochemistry. So, I can see here, this is bulky, right? That's not right. So a bulky base means that my major product will not be the most stable. It will be opposite because let's go through something like that. So my most stable product will be formed if I take this hydrogen and this chloro group and make a double bond here. Okay. But because this base is so giant and chunky, it can't get in here without touching this methyl group and causing steric hindrance. Because these groups are big, they'll get in the way with this. This electron cloud will be touching this electron cloud. They're going to repel each other. It's going to cause a bond strain. We don't want that. So it's not going to come and take this hydrogen, even though that would be the most stable. It's instead going to come on the end, where it's nice and open and free, and take this hydrogen here and make this product here.
So when we solve something like this on the exam, or even the homework, does he just want us to show what the actual product would be?
Mm-hmm.
Okay.
Yeah, you don't have to show like all the. Sometimes I'll ask for all the possible products and then give a major one. But in terms of if you're writing a mechanism, I normally just ask you for the mechanism of the major product.
Okay.
So, because the base is bulky, it's going to come and take this hydrogen on the end here. The CH bond will break. Those bonding electrons will go to form a double bond here. And at the same time, because the E2, that chlorine carbon bond will break. So I'll make that. Chlorine will come off as an anion, and then we'll have T-butanol. But we don't really care about those. Does that make sense? Okay.
The bottom one, it doesn't matter because the basis, or the, it's not bulky.
Right. So in the bottom case here, hydroxide is not a bulky base. So now I am free to get into that middle carbon and take this hydrogen because hydroxide is small and it can just come in here and it's not going to bother this methyl group. And then I can make the most stable product. So I'm going to take the hydrogen, CH bond will break, form the double bond in the middle now because we're making the most stable product. And then the carbon chlorine bond will break, chlorine will come off. Again, chlorine will come off as an anion and will form water. Okay, so this is the most stable product. Okay, but that is only the major product if we use a non-bulky base. This is less stable, but it'll be a major product if we use a bulky base. Make sense? Any questions? Okay, so stereochemistry. This I feel like is like one of the things I had the most trouble with in organic. This whole like rotation degree thing is kind of tricky to visualize. So here we have this substrate, right? This is my leaving group. This bromo group is my leaving group, and I want it anti-coplanar with a hydrogen. Okay, I don't have that right now. This is an eclipse formation, right? So you can tell something is eclipsed or staggered if the things that are in all the same plane are like this, then it's eclipsed. If they're anti-coplanar like that, then it's staggered. So I want this hydrogen in the same plane as these carbons and the bromine, but it's in the back right now. So I'm going to have to rotate it to get it anti-coplanar. So I had a lot of trouble with this personally, trying to visualize like where to rotate it, where things go after that. So I found that this is a good way to visualize it. So I use Newman projections for this. So if I'm looking at this carbon here as a Newman projection, I'm not going to draw the back because we're not moving that and we don't care. So I'm just drawing the first carbon as a Newman projection. I have hydrogen down here, okay? I have a methyl group here, and hydrogen here. So So pretend this yellow line, that's the plane, and then here to the right is the front, and to the left is the back. Okay, does that make sense? We have this hydrogen in the plane, and it's going down, so that's this hydrogen here. This hydrogen is in the back, right here, and then this methyl group is in the front. Okay, so what I want this hydrogen here. Okay, so I want to rotate all of that so I can get that hydrogen in the plane. Okay, and from here to here, so this is a circle, right, and I have 3 dividers in the circle. So from here to here is going to be 120 degrees. So if I'm just going halfway between the two, it should be 60 degrees, right? So I'm going to rotate the whole thing 60 degrees. And then I'll end up with hydrogen in the plane up top. And then the methyl group will stay in the front, but it's just down in the front now. And then this hydrogen that was in the plane gets shifted back. So here's the plane, front of the plane, back of the plane. Does that make sense? Okay. So after I rotate, I should end up with this right carbon has no change. But now I have my hydrogen up and in the plane, so now I have anticoplanar. Okay? So my hydrogen that was in the plane is now back in the back, and then the methyl group is now down in the front. Does that clear things up at all? I don't know if you guys will have trouble with this, but I thought it was very confusing when I was in organic. Right, because this here, this is syn-coplanar. I want them anti-coplanar. So they're in the same plane, but they're on the same side of the same plane. I want them on opposite sides of the same plane. So I hypothetically could rotate that hydrogen that's already in the plane to the other side of the plane, but that would be more complicated than if I just took the hydrogen that was in the back and rotated 60 degrees in the plane. Does that make sense? Yeah, so the bromine is fine where it is. We want the bromine there. We're not messing with that right carbon at all. We're only rotating the left. Does that make sense? Everybody following me?
So,
What's our goal exactly?
So your goal is to get it anti-coplanar. So it won't always be 60 degrees as well. So that's also a part that's kind of confusing. So right here, we started in eclipse formation, right? So this syn-coplanar means eclipsed, okay? And we wanted to end up in staggered, okay? So eclipsed to staggered, you'll rotate 60 degrees. But I could have started with this methyl group anti-coplanar with the bromine, which is anti-coplanar, it's staggered, but it's not the staggered I want. So if you start with a staggered you don't want, and you have to rotate it to a different staggered, then you'll rotate 120 degrees. But if you're starting in eclipse and you want to go to staggered, then you rotate 60. Does that make sense?
Yeah.
Any questions? Okay.
So that's anti-coplanar.
Yeah, so now this is anti-coplanar, and now I can do any two reactions.
How do we
so can we
indicate?
just make stuff up and make it look anti-coplanar?
Yeah, no. No, you have to show that you're rotating.
Oh, you guys just can't do it.
You could try, he would maybe.
If they do this, then they're anti-coplanar.
But it has to be a high frequency. Yeah, how do you achieve?
Yes, that's what she was saying, it's like.
Yeah.
Yeah.
Okay.
Kind of like this. I see what you're saying now. I didn't understand what we were looking at.
Yeah, so yeah, if it looks like that, anti-coplanar. If it looks like this, then it's thin coplanar. I don't want that, I want this. Okay, but this, I only want this if it has hydrogen and a leaving group, okay? Because I could have anti-coplanar, but it's not the right anti-coplanar with things that I don't want on either side. Then you'll have to rotate the 120. What is it? So I don't think of any, I can't think of any examples that he has ever given where both of them are wrong. So one of the carbons, if as far as I remember, should be right, and you should just have to rotate one. I can't remember anywhere you have to rotate both.
So would we have to tell him, like with a Newman projection we're rotating, or
No,
just like?
this is just what I came up with to visualize, because if you don't have that, what I would do is I would sit there and take the test and like try to figure out with my fingers like where things are going. Because I find it difficult to go from here and then try to visualize what it looks like after you rotate. So I just do that I think it's easier to
Okay.
tell where
I
it's
just
going.
didn't know if that was,
No,
this is visualization.
yeah. So you would just have to show this arrow, rotate 60 degrees, and then this. That is what you have to show. Yeah. You do have to show your rotating and by how many degrees, but you don't have to show this. This is just for educational purposes. Follow me? Any other questions? Okay. So now that I'm an anti-coplanar, now my base can come in and do things. So my base will take hydrogen, CH bond will break, make a double bond, CBr bond will break, and then I form product. And then this would have cis trans. We know the trans would be more stable, so I'm not gonna write that out. But so trans ice would be more stable.
Forgive me, but I can't remember. Does stereochemistry matter with the bulky or non-bulky?
No. Yeah. So this doesn't matter bulkiness, non-bulkiness, because we have this anti-coplanar stipulation
makes
thing.
sense.
It doesn't
Okay.
matter how big this is; it can still get here,
I'll
no
remember
problem.
that. Okay.
Any other questions before I move on? Okay. So, after dehydrohalogenation, talk about acid catalyzed dehydration of alcohols, which should be somewhat familiar to you. We did this earlier last semester. But it is another type of beta elimination where water is eliminated from an alcohol and we form an alkene. So typically you'll have secondary, tertiary alcohols follow an E1 mechanism, and then only primaries will follow E2. Heating is required. I'm pretty sure you guys have done this in the lab before. So you have to heat. And then you also need an acid to protonate OH group to convert it to a good leaving group. That's not part of the elimination mechanism. So that's just, you need to make a good leaving group for the elimination to happen. So, I'm pretty sure is this the one you did in lab? It is, isn't it?
Mm-hmm.
Yeah. So, we've done this mechanism before. So you have sulfuric acid, which is more or less just a proton. So your first step is going to be to protonate the OH group. So a lone pair of electrons on oxygen will take your hydrogen. To make OH2, which is water, and that will form a positive charge around oxygen. So now because of oxygen has a positive charge, now it's not happy anymore, it wants to come off. So that carbon-oxygen bond will break, and we'll lose water. And because this is secondary, it follows E1, right? So after water comes off, we'll form a carbocation on that carbon there. There's secondary carbocation. So in this case, it doesn't matter which beta carbon it is because they're both equal. So that CH bond will break, form a double bond here, which will neutralize that positive charge of carbon. So we lose hydrogen here and form this. So there are a few different ways to show this mechanism. So sometimes he'll show the counter ion to sulfuric acid. Oh, that's not. Oh yeah, it looks good. Is that it? Right? Yeah. So sometimes he'll show the counter ion of sulfuric acid, take the hydrogen, or if you remember, we did examples where you just use the H plus as the catalyst as opposed to writing out all of sulfuric acid. So you can do it either way. It's up to you. I would say probably in elimination in this chapter it would be safer to use sulfuric acid and show the counter ion, just because it shows something taking the hydrogen as opposed to it's the hydrogen coming off. But and there are examples of that in the PowerPoint. But it means the same thing either way.
So do we have to show? You said we have the option of showing the calendar.
Normally, yes, but I'm hesitant to say that now just because this is the elimination chapter.
Okay.
So now that I'm thinking about it, you probably actually let's just go back and do that. I don't remember the structure of sulfuric acid. So we have an O2 there to make that O4. And then there should be another hydrogen, and I don't know where it goes. Can somebody look that up for me? Structure of sulfuric acid, because I can't remember. Yeah. Yeah, I think you're right. Okay. So it should be 1, 2, 3. Right? That's right, right?
Yeah, is it always?
Yes, sir.
There's this,
Ah, yes. Okay. Thank you. Okay. That's ugly. Hold on.
because there's 4
Yeah. So sorry. Okay. So sulfuric oxide's here. So it'll take a hydrogen from one of these, break that OH bond, and then it'll form an ion there. Same thing. So down here. So this would be the counter ion, where we took that hydrogen here. Now this oxygen has a negative charge, and now that oxygen can take this hydrogen, and then we form the double bond, neutralize positive charge. So I'll probably show it like that. I don't know, maybe ask them that. But to be safe, this would be a safer route to show the sulfuric acid. Did I just confuse all of you, or are we okay? Okay.
I'll ask him.
Yeah, the other one is much simpler. I don't know. He doesn't normally show the exact structure, but I don't remember how he writes it without the structure, because I remember, like, I don't remember how he writes it. Look in the PowerPoint and see how he writes it another time, because I don't remember. But I know he normally writes that kind of right. Okay, can we move on? You all right? Okay. Okay, E2. So, the same thing. We need to protonate first. I'm just going to do it the other way because I don't remember how to do the other way right now. And I don't want to confuse you. Okay. So, because this is E2, it's going to happen all in one step rather than form a carbocation. So this CH bond will break, form a double bond here, and then this bond will break at the same time. And we'll end up with ethene, and then water will come off as our byproduct. Does that make sense? So, also how you can show it with just the hydrogen here on the other one. Actually, I'm not even going to say that because it's just confusing. Never mind. But, never mind. Okay. Any questions here? Okay. Are we going to move on? Okay. So next thing we went over, carbocation rearrangement. So, this you'll have to look out for from now on. Pretty much anytime you make a carbocation, you'll have to check if it can rearrange. So if there is a possibility it will rearrange, it will do that spontaneously. So you can either rearrange methyl groups or hydride ions, and they'll shift to adjacent carbons to make more stable carbocations. So do you remember that question in the book from an assignment last semester that you couldn't figure out how to do because
Yes.
yes, that was rearrangement, which
Oh.
he was like,
You
yeah,
made
I've been
that a
careful
lot.
not to include that. Yeah, it's in that assignment. So that's what happened in that one question where you didn't know how to get to that product because it didn't make sense. This is what happens. So rearrangement can happen in E1 and SN1, and SN1 will come up on this test, so you'll have to brush up on that a little bit. Just not like a crazy amount, but just look out for it. Substitution is not gone. Okay. So this is E1, so the first step in the mechanism is leaving group leaves. So form a carbocation. Okay. So this is a secondary carbocation. But I have this handy dandy little carbon here. There's two methyl groups on it. So if I just take one of these methyl groups and switch it on over here, the methyl group and the positive charge will switch places. And then what do I end up with? Right. So yeah, I'm gonna move this methyl group over. So keep that methyl group here. This methyl group is now here. Okay. So this positive charge is now going to switch to this carbon.
And he said just to draw the more stable, like you don't have to show, like, moving it. Because that's what I kind of tried to ask.
I don't remember what he said. I think.
Didn't he say to write H rearrangement?
Oh, yeah.
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 Yeah, I think you do need to show rearrangement.
Okay.
So I normally just write rearrange
Okay.
to show what's happening. So now I went from a secondary to a tertiary carbocation,
Right.
which is more stable. Does that make sense?
Yes.
Okay. So now my base can come in. Remember this carbon here has a hydrogen. So now my base is going to come in, take that hydrogen, break the bond, make the double bond. And this would be my product, which would be more stable than the product with the secondary carbocation because this one has less hydrogen around it. Does that make sense? So more stable carbocations make more stable products, which is the driving force for the reaction. Make sense? Any questions?
And then wouldn't water be a byproduct?
Yeah. Yeah, I normally leave out the byproducts sometimes just because they don't really matter. But yeah, water would be a byproduct. Any questions? Okay, so SN1. Your first step is still the same. The leaving group comes off. Okay, so this is secondary carbocation. What can I do here?
Put it on the second carbon in the chain.
So, do we see that if I move this methyl group, because that would maybe be your first thought, is move the methyl group. If I move this methyl group here, I would just end up with another secondary, okay? But I have a hydrogen here, so I can
Switch somewhere.
move this hydrogen
Yeah.
over to that other carbon.
Yeah.
So the hydrogen and the positive charges switch places. So, am I missing a hydrogen somewhere?
I don't think so.
Yes, I am. Sorry, I was missing a hydrogen. That one should have had another hydrogen this whole time. So sorry. Okay. Okay, so now I move this hydrogen over. So now that carbon that originally had the positive charge now has 4 bonds. It's happy. But now I took a hydrogen from this one. Now that one has a positive charge. And now I have a tertiary carbocation. Does that make sense? Okay. And now, so this is SN1. Now my base can come in and just make a carbon-oxygen bond. And then I make an alcohol. I'm running out of room, but you know how these reactions go. And this will be my product. Okay. Any questions? Feel good? All right. That is all I have. If you have any questions about homework,
I started, yeah.
I think
Yeah,
I don't know.